everyone. Thank you for joining me today. My name is Wincy, and today I'll be talking about black holes. Here's the outline of my presentation. We'll first start with the definition of black holes, followed by their formation process, classification, and detection methods. Then we'll explore the structure of black holes and conclude with their ultimate destruction. Let's get started. So, what exactly are black holes? A black hole is a region in space where the gravitational forces are so strong that nothing, not even light, can escape. They are not to be confused with wormholes, which are theoretical tunnels connecting different points in space and time. The immense gravity of black holes is caused by a large amount of matter being compressed into a very small area. Black holes were first predicted by Einstein in 1916 through his theory of general relativity, and the term black hole was later coined by physicist John Wheeler in 1967. There are three key properties of black holes: the event horizon, which is the boundary beyond which nothing can escape; the interior space, where time and space are severely distorted; and the singularity, the core where gravity and density become infinite. Black holes can come in any imaginary size, and the size of a black hole depends on the mass it contains. The two equations here provide a way to calculate the size of the event horizon for any given mass, or the vice versa. Let's move on to how black holes are formed. The most common type is a stellar black hole, which forms when a massive star, with a mass greater than 8 to 10 times that of our Sun, exhausts its nuclear fuel hydrogen and undergoes a supernova explosion. The core of the star collapses to a point of infinite density, known as singularity, and an event horizon formed around it. However, not all stars leave behind black holes. Stars with lower birth masses leave behind a neutron star or a white dwarf. Another kind of black holes formed are called supermassive black holes, which are found at the centers of most galaxies, including our Milky Way. They can have masses ranging from millions to billions of solar masses. While the exact formation process is unknown, one hypothesis suggests that they are formed by merging smaller black holes or through the direct collapse of massive gas clouds in the early universe. The third types of black holes, intermediate black holes, are thought to form when stars in a cluster collide in a chain reaction, while the fourth type, primordial black holes, are hypothetical black holes that may have formed shortly after the Big Bang. Now, let's classify black holes. They can be categorized by their formation or their masses. By formation, we have stellar black holes, which is formed by the death of massive stars, and we have supermassive black holes, which form through merging smaller black holes or the collapse of gas clouds. And we have intermediate black holes, which are created by star collisions. And we have primordial black holes, which may have formed after the Big Bang. By mass, black holes range from micro black holes, which could be as small as a Planck mass, to primordial black holes, which is a fraction of a gram to thousands of solar masses, to stellar, which is approximately 5 to 20 solar masses, to intermediate, which is approximately 100 to 100,000 solar masses, or to supermassive, which ranges from hundreds of thousands to billions of solar masses. For the detection of black holes, the first black hole identified is Cygnus X1, as shown in this photo. Humans saw signs of it in 1964 when a sounding rocket detected the celestial sources of X-rays, and the black hole was identified in 1971. It was a stellar mass black hole, which is formed by the collapse of a massive star. Black holes are invisible because they emit virtually no light. However, we can detect them through the effects they exert on their surroundings. There are many methods that can be used, but I just talked about three of them. The first one is the accretion disk observation. This method involves observing X-rays emitted by the superheated material in the assertion disk as it spirals into the black hole. The intense gravitational forces compress and heat the material, making it emit high-energy X-rays. Space-based telescopes, such as the Chandra X-ray Observatory, are used to detect these X-rays. This method is crucial for identifying stellar black holes and studying active galactic nuclei powered by supermassive black holes. The second method is the gravitational influence. In this method, we study the motion of nearby stars or objects to detect the gravitational pull of an unseen massive object, which we infer to be a black hole. This technique has been seen instrumental in confirming the existence of a supermassive black hole at the center of our galaxy, Sagittarius A. Astronomers use telescopes that track star movements, such as the Very Large Telescope (VLT), to monitor these changes over time. The third method used is the gravitational wave detection. This groundbreaking method captures ripples in spacetime caused by the mergers of black holes. These ripples, known as gravitational waves, were first detected in 2015 by the LIGO Observatory. Gravitational wave detection is revolutionary because it provides direct evidence of black hole collisions and allows us to study phenomena that cannot be observed with electromagnetic signals. Instruments like LIGO and Virgo have opened a new window into the universe by enabling us to hear these cosmic events. Here are some other detection methods. Next, let's delve into the anatomy of black holes. The main parts of a black hole is shown in this photo, on top of the three main parts mentioned before, which are the event horizon, the interior space, and the singularity. The accretion disk, which is a rotating disk around a black hole formed when a black hole pulls in matter from a nearby star or gas cloud, is also an important structure for the detection of black holes. Lastly, for the destruction of black holes. According to Stephen Hawking, black holes emit radiation, a process known as Hawking radiation. Over astronomical timescales, this radiation causes black holes to slowly lose mass and eventually evaporate, returning their energy to the universe. This process can take an incredibly long time, on the order of 10 to the power of 100 years, or Google. As a black hole loses mass, its rate of particle emission increases, leading to a final burst of radiation. This is the end of my presentation. Hope you have enjoyed it. Thanks for your time and listening. And here is the reference list. Thank you. Bye bye.